Okay, so we've been talking about nuclear chemistry here, and we've been talking about that. Yeah. So we talked about balancing nuclear equations, and remember that when we do balance nuclear equations, we're really looking at two things to make sure that they're balanced. Again, because we do not have conservation of elements, because all these reactions pretty much involve everybody that's in the nucleus. What we're looking to balance is when we add up all the mass numbers on the left-hand side, it does need to equal all the mass numbers there on the right-hand side. And also same thing with our atomic number. All the atomic numbers on the left-hand side does need to equal all the atomic numbers there on the right-hand side. And usually, again, in this situation, you may be missing something, and the atomic number, which tells you pretty much what element it is, because the number of protons is usually a good place to sort of start. And you can use the periodic table, obviously, to figure out what the missing atomic number is. Remember, it could also be a particle. We have different particles that we run across, things like the alpha particle, the beta. You could have gamma. You could also have a proton, also a neutron, and all these other sort of particles along the way. In addition, if you have it in words and they talk about some type of decay through some type of emission, then those particles usually will end up there on the product side. If it's some type of bombardment or electron capture, then those particles will most likely end up there on the reactant side. But probably most of the time, you're going to have probably your particle there on the product side coming off, and you can basically figure out what is going on. Again, we really do not have the conservation of elements, because as we saw in that previous slide, what we're doing in a lot of cases is converting maybe protons to neutrons or neutrons to protons. And the process of doing all that will release these certain particles like alpha particles, beta particles, and so forth. And in some cases, we may not have an overall change in the mass number, but we will have really a change in the mass number, because we may lose a proton but gain a neutron. So there's a net no change sort of happens in the mass number. But there is sort of an exchange, obviously, of particles that are happening. We were talking about stability, I think, last time, where we ended, and we were looking at the neutron to proton ratio for stability. There's that valley of stability, sort of a nice, our belt of stability, stable sort of situation. If you calculate sort of the neutron to proton ratio, and again, if you're kind of a little bit too high, it will go under a decay process to sort of bring that ratio back down towards the more stable valley stability. Or if you're a little bit low there, it will kind of bring the ratio up there by going through a possible decay process. Remember, you could do a beta decay if you're a little bit too high, and electron capture or a positron emission for the other if we're too low. Again, in that case, as we saw, you could do either one, the positron emission or the electron capture. You'll end up with the same product at the end, as they basically end up the same way along the way. We also talked about the idea that if you are doing a problem like this, you just have to do the decay sort of process once. It may not give you a perfect ratio when it's all said and done, but it definitely should sort of move you back to a good ratio, or a better ratio, I guess. And again, if we're too high, we're going to do that beta decay or positron emission, electron capture for too low. But here was our breakdown, and it does go by atomic numbers. So 1 to 20, a stable ratio again is 1, 1.25 as you approach 20 to 40, and 1.5 there basically as you go from 40 to 80 in terms of stability. And as we talked about last time as well, we're going to use these as pretty much hard cutoffs. So again, if it's either that number or not that number, it'll be too high or too low. Again, there is some gray area as you're transitioning from one sort of atomic number set to the next, but we'll try to take that out. So I think we did this guy, right? So We did this one or we did not do this one? I don't think we did. So why don't we do this one? Predict whether or not Krypton 85, Krypton's 36, will be stable. And if not, predict what will happen and what mode of decay it will undergo. Okay, so let's take a look. So we have Krypton 85. Remember, that is our mass number there. The way it's written, we could get our atomic number there from the periodic table. Number of neutrons in this case would be 85 minus our atomic number, which is 36. That's going to give us a number there, or it's a couple of digits, 49. Our number of protons here would obviously equal our atomic number, which is 36. That will give us an N to Z ratio there, 49 divided by 36. Gonna get us a 136 in terms of our ratio. This is 36, which means it falls between the 20 and 40 sort of range, where the acceptable ratio of $1.25 there, right? So in this case, it looks like perhaps it's a little too high, I guess. It might be high. So in this case, it needs to come back down. So in this case, it's going to do a beta decay. So if we were to write our equation of what would happen in this case here, we would have 8536. It's going to emit a beta particle, which again, you can use that or the E as the symbol. It is -1, which means we do need to go one more there on the periodic table. So that's going to be a 37 to get us 36 on the bottom on both sides. That's our friend RB. Up on top, we're going to have an 85, and that is what we should end up with. We could check just to make sure that we are sort of coming down to that. If we look at the number of neutrons in our new guy here, that's 85 minus 37. So that's going to get us here 48 divided by 37, which is the number of protons. And we're now down to roughly a 130. So again, we didn't hit perfect like we were talking about earlier, but we are moving in the correct direction, right? We went from 1.36 and we're moving down towards that 1.25 ratio. So again, you may not always hit like a nice perfect ratio. I think we hit perfect on the previous example when we did the sodium, but you won't always sort of hit perfect. And you don't have to keep going until you get perfect or anything like that. Any questions on N to Z ratio here? So this is one way that we could look at stability, and if you want to calculate it, you can, which is a good way to look at stability. There are other methods that we look at when we're looking at stability to try to figure out if something is stable or unstable. So let's talk about a couple of other ways that we just kind of quickly look at, maybe without a calculation. And there you go. That's good. They agree. That's perfect. Let's talk a little bit about some other things that we look at in terms of stability. Most stable nuclei will have either even numbers of protons and neutrons. So if you look at this table on the bottom here, that's sort of the ideal situation. If you see even protons and even neutrons, you can see there's like 157 stable nuclei that have that sort of arrangement. The next best situation is even number of protons, odd number of neutrons. And you can see it drops down to about 53, followed by odd number of protons, even number of neutrons is about 50. Really, your worst situation in terms of stability is if you see something that has basically odd of both protons and neutrons. There's only like 5 that are sort of stable with that arrangement. So if you're not maybe just want to quickly look at something and try to decide, do you think it's going to be kind of stable or not? You could look at whether or not it has even or odd number of protons and neutrons. And again, worst case scenario, odd of both, kind of best case scenario, positive of both in those cases. In addition, if the total number of nucleons, and by the way, nucleons is a word that's used a lot in nuclear chemistry, it means really the particles in the nucleus. So that's your protons and neutrons, right? It's basically a nucleon. It's kind of your mass number. If they add up to a magic number, then the nucleus is more stable. It's kind of the idea of like they add up to sort of like a noble gas configuration. You have a lot of stability when either the neutrons or the protons are 28, 20, 28, 50, 82, and your mega number there is a neutron of 126. And these are some numbers of where things are really sort of stable if they have either neutrons or protons that have those type of numbers. And those are sometimes referred to as the magic numbers. So I would say in terms of stability, looking at the N to Z ratio is a really good way. Also, a lot of people, again, will kind of do the odd, even type of situation. We're going to look at something a little bit later on as well, where we look at stability through another sort of measurement. So let's talk then a little bit about decay series. So in a decay series, what will happen is a nuclei will continue to go through the decay process until sort of a stable nucleus has been reached. And the starting sort of nuclei, again, is what's sometimes referred to as the parent. The daughter is sort of what comes afterwards. Now, if you have a stable nucleus and it starts to go through this sort of decay process, there's two ways that you can sort of figure out what you will end up with at the end. You can do basically just reactions like we did, balancing equations, so one right after the other. And if it happens to be beta decays or alpha decays that are involved, you can basically subtract them from the mass number 4 for every beta alpha decay. So for every alpha decay, your mass number, you're going to subtract 4 from it. And your atomic number, you're going to subtract 2. And for every beta, you're going to add 1 to your atomic number. So if you're maybe just interested at what you would get at the end of the road there, you could kind of just do it mathematically and figure out what you'll end up, but you could also do it in a series of reactions. So let's take a look at both ways here. So let's just say, for example, here we started with uranium 238, and that'd be 92. And let's just say we'll just do a very short little decay pattern here. Went through alpha, beta, and then we'll go with alpha. So one approach that you could do this is really just write the equation. So for example, the first thing that would happen here is we would take our 238 and our 92, and it's going to go through an alpha decay, which means our alpha particle should be on the product side. And maybe a 2, we'll make that a fancy 2 now. There we go. And here, the first thing that we would produce as a result of this alpha decay is we would end up with 90, and 90 there is TH. And up on top, we would end up with 234. What will now happen in this sort of decay process is the new guy that you just made here will then go through a decay process, next decay process. So we would actually start with what we made there. And then this guy would go through the beta decay. And that means I need to add 1 back. So that's a 91, which will give us PA. And that will give us 234. Once again, it's going to be our product here that will continue on in this decay pattern. So we'll take our product there. And that guy is also going to go through in my little series here, another beta decay, which means we're back up to 92, which is uranium. And we're at 234. And lastly, this last guy that we made here will go through my final step, which is an alpha decay. And again, we'll have our alpha particle here. And that's going to give me a 90 and a 230. And once again, 90 is RTH. So this is one way that you can sort of figure out what you would get, obviously, at the end here. And this is also a really good way if you're also interested in what you would get after each step along the way, right? So you basically have the answer there after each step. Now, if you were doing this and you were just interested really in what you're going to get at the end of this short little process here, you could just add up what you have going on here. So we started at 238, which is our mass number, and our 92, which is our atomic number. And in this case, we went through two alpha decays. And that means for every alpha decay, we're going to subtract 4 from the top number, which would get us 8 that we're going to take away. And we subtract 2 for every one from the atomic number, which would be 4 on the bottom there that we get rid of. And remember, for every beta decay, we're going to add 1 back to our atomic number, which means we would add it back there. That's going to give us 230. And that's going to give us basically 88 plus 2, which is 90, which gets us to our end product here. So if it's just alpha and beta decays, you can kind of mathematically figure out what you get at the end, or you can kind of go step by step there through each of the processes there, where your product becomes like your reactant there in the decay process in each case. Any questions on that there? So obviously this thing would continue to go through the decay process until it pretty much hit something that was stable. And that's somewhere around lead all the way down the road here. And that's the decay process that occurs for something like uranium that we just did. And as you can see, it's a pretty long decay series, and it can sort of separate out into 2 different processes. But they both will end up over here at lead, which is its stable sort of nucleus here. And again, if you were just doing this decay process and want to know where you would end up, you could do it mathematically, or again, do really your equations. And as you see, and it's very common in nuclear chemistry, not everything always happens the same way all the time. There's different pathways that things go through, or different decay series that things end up at, depending on the situation. Any questions on a decay series here? So then let's talk about our favorite thing, which is kinetics. Throwback day. Here we go. So kinetics, I know we're going to start over again. We're just going to do it again. It was so much fun. We're going to start at the beginning. Chapter 12 for kinetics. So kinetics, radioactive decay follows our friend first order kinetics. Yes, we remember those. If not, I guess it's a good review for the final, I suppose. First order kinetics is pretty much what all radioactive decay follows. And frankly speaking, it is still the same equations that we used in kinetics chapter. So as you remember, I'm sure that is the integrated rate law, where the natural log of A is equal to the natural log of A naught minus KT, where the half-life, right, is our natural log of 2 divided by the rate constant, or 0.693 divided by the rate constant. And the important thing that you also remember is that the rate constant has units of 1 over seconds, right? Or 1 over some type of unit of time. So if you want to ignore all the other symbols we're going to see, you can basically just throw back to those equations. It's the same equations, but it's nuclear chemistry, so they like to use their own symbols sometimes. So they'll sometimes use some different symbols, but frankly, it's those same equations that we used previously, so you can just put it in there. Something different, though, in terms of how we use these equations is when we're doing kinetics, typically the units that we were using in the concentration were molarity. So different here is you don't necessarily have to use molarity. You could use actually grams on both sides, milligrams on both sides. You could use percentages. You could also use rates of radioactive decay. So how many disintegrations per minute can be used on each side? So you really, in terms of slight differences, you pretty much could use any unit you want in each of those sides there. It doesn't necessarily have to be molarity or anything like that, like we kind of did with kinetics. It can really be any units, as long as they're the same, obviously, on both sides, so that everything cancels. Also, a couple of other different things is they don't really call it the rate constant here. They call it the decay constant, but it's pretty much the rate constant. So they'll call it the decay constant. and N for nuclide, because we're talking about nuclides sort of radioactive decaying. So instead of like concentrations, that is what those things are. And once again, you could use rates of radioactive decay instead of sort of concentrations. I would say probably a little bit more also is the use of both of these equations together. Yeah, so the use of both of these equations together is very common, because in radioactive decay type problems, they oftentimes will give you the half-life. So a lot of times you also use the half-life equation to figure out the decay constant, and then kind of go into the actual integrated rate law to solve for whatever you're trying to solve for. So I would say probably these equations are used kind of together a little bit more than we did when we did regular kinetics sort of earlier on. We still have our same graphs. So that's our natural log of our concentration versus time, right? Gives us our linear relationship where the slope is still equal to negative of the decay constant. Just to have more fun, instead of using K for the decay constant, some books will actually use lambda for the decay constant. And again, a reminder here that T is time. Also, you want to make sure, as we talked about when we did it the first time around, these two units in terms of their time is the same units as well, so that everything cancels out correctly. So half-life obviously is the time it takes for half of whatever you started with to go away. So again, if you started with 10, after the first half-life, you have 5. After the second half-life, you have 2.5. And then I need a calculator after the third half-life, but you know, you keep dividing it by 2. But some things have really long half-lives, and some things have very, very short half-life. So clearly, nobody's around probably for any of these half-lives. I imagine that's a lot of years before half of it goes away. But you can also see some things are super fast type of half-life, which means it'll be gone very, very quickly and not so radioactive. And obviously, different types of emitters and decay processes that go through it. So let's try one here for old time's sake. If you have a 1.35 milligram sample of plutonium-236, calculate the mass that will remain after 5 years. And it's not on there. Oops. I feel like, do you have the half-life on your notes? That might be helpful, maybe. There it is. I think the half-life there is 2.86 years. That might be a helpful piece of information, I imagine. That works the same. So I'm gonna go natural log of A is equal to our natural log of A naught. And as we mentioned earlier, once again, you don't have to use molarity like we kind of did there in kinetics. Again, you can use any units that we have. So we really have the initial amount there of 1.35 milligrams. We're really looking for our final here. And we do have a time of 5 years. So we do have this, we have that, we are looking for that. So once again here, we are kind of missing the decay constant in this case. So that is where the half-life will come into play. We can use our half-life equation here to basically figure out our decay constant, and then we'll have everything that we need to really solve this. So the decay constant in this case would equal the natural log of 2 divided by the half-life. And in this case, that would be the natural log of 2 divided by 2.86 years. And that's going to get us a natural log of 2 divided by 2.86 years. That's going to give me a decay constant of 0.242. And it is reciprocal years, right? And it doesn't have to be seconds either in this case, right? And years are okay because actually my time is in years. So that all works out. So that's what I was saying earlier. You do want to make sure that those units of time and both the decay constant and obviously the time part are the same units. Otherwise, you should do a conversion to get them into the same units. So now that I did that, I really do have everything I need to just plug into my first order equation here. So my natural log of A is going to be the natural log of my 1.35. And again, you could slap it right in there with those units. minus our decay constant that we just found, which has reciprocal years, times our 5 years. And again, this is why it's important, so that our units there cancel out. That's going to get us, if we kind of clean up the right-hand side here, a natural log of 1.35 minus 0.242 times 5. And that's going to give us that natural log of A is equal to minus 0.9099. We'll call it. And to get rid of natural log, we're going to E both sides, right, to do that. And that's going to get rid of the natural log over there, which gives us a concentration. And again, we're not going to do anything with the sign of it. We're just going to take the E of whatever sign it is on that side. And that's going to give us something like 0.403. Now, in terms of the units, because we threw milligrams in there, those would also be the units on the back end here of our final amount. Any questions on that there? Now, it does make sense since it's less than what we started with. If it was more than what we started with, that would not be good. And it also makes sense if you just think about it, that's 5 years, which is roughly just under 2 half-lives. And that's a little bit more of what you should have after 2 half-lives or before 2 half-lives. So again, it's sort of in the right area where we would expect. Any questions on that one there? All right, let's try another one here. Radon 222 is a gas that is suspected of causing cancer. Assuming no loss or gain from leakage, if there's 10.24 grams in your house today, how much will be there in 5.4 weeks? And the half-life there is 3.8 days. So what you come up with. Okay, so once again here, obviously the nice thing is we don't have to think about what equation to use because it all should be first orders. So we'll use our first order here and we'll lay up both of them here. So in this case here, once again, we do have the initial amount of 10.24 grams. And we want to know after 5.4 weeks, how much will remain. So we do have the half-life given to us as well, which is 3.8 days. So here again, we do have the time. We have that. We're looking for that. We again are missing the decay constant, but we are given the half-life, so we're going to use that equation to get it. Here we do maybe want to think about units as we do have some different units happening there. So at some point you do need to do a conversion between them. So I'm just going to convert out the half-life into weeks. You obviously could take the weeks into days, whichever way you want to do it. So I think there should only be 2 days in a week, no, 7 days in a week here. That means that we will have for our half-life divided by 7. 0.543 weeks. So now that I have that, I can solve for the decay constant, would be the natural log of 2 divided by the half-life. And that's going to be a natural log of 2, 0.543 weeks. Once again, if you left that in days, you'll have obviously you'll have a different answer than what I'm going to put up here. But it should all work out the same at the end. You'll have 1.28, again, reciprocal weeks here if you did it this way. Now that we have that, we could go our natural log of A will equal our natural log of 10.24 minus 1.28 reciprocal weeks, which works good with my 5.4 weeks of time. The weeks here will cancel, and that's going to get us here natural log of 10.24 minus 1.28 times 5.4. Going to give me the natural log of A is equal to minus 4.586. Again, I'm going to E both sides there. And that's going to give me a concentration here of, and once again, not doing anything with the sign, just going to leave it the way it is. 0.0 102, and these would be grams in this case, give or take. Yeah. Any questions on that one there? So again, obviously, first order kinetics, similar to what we did before, but probably again a little bit more integration of both of those equations together in problems as obviously as nuclear decay. So giving you the half-life is a very common sort of approach there. All right, we could also calculate things and use radioactive decay to date how old things are through radiocarbon dating. Carbon there is 5730 half-life years. You can also use uranium, which will decay out to lead, and it has a half-life of 4.51 times 10 to the 9 years. Sometimes you can use the difference between these two to figure out how old something is, how much remains. So if we were going to do a problem like this, let's take a look at this one and sort of explain what we are looking at here. An ancient skull gives 4.5. The units here are actually disintegrations per minute, and this is actually per gram of carbon. So that's not Celsius. Yeah, so that's actually per gram of carbon. And that's important because it's pretty much telling you that's going to be your half-life for carbon here, which is our 5730. So our half-life here would be 5730 years, again, because it's carbon there. If a living organism gives 15.3 disintegrations per minute per gram of carbon, how old is a skull? So if we take a look at our first order here, we're looking for how old it is. We have really our initial and final sort of rates of radioactive decay, which again, much like how we just threw the grams and milligrams into this equation, we could actually throw the rates into this equation. So again, works the same way. We are again here missing our decay constant. So we'll use our half-life of natural log of 2 is equal to our half-life here to get that. So our initial sort of rate of radioactive decay is a living organism. Yeah, so that's living. So that's going to be 15.3 disintegrations per minute per gram of carbon. And our final is like probably the dead thing here. So that's going to be 4.5 disintegrations per minute per carbon here. And obviously that is less radioactive decay happening, right? So it's smaller, which means it's been around a lot longer, so it's not giving off as much radioactive decay in that case. So we're looking for time in this case. So using our half-life equation here, our decay constant once again will be a natural log of 2 divided by our half-life, and that's going to give us the natural log of 2 divided by 5730 years. So that will get us natural log of 2 divided by 5730. It's going to give us 1.21 times 10 to minus 4 reciprocal years as our half-life, our rate decay constant. So putting in our values here, the natural log of our final, which is 4.5, equals the natural log of our initial, which is 15.3, minus our decay constant, and we're looking for time. So since we have years here, that is what we're going to end up with really in our units. So a reminder that I personally will do the natural log of 4.5 hit equals, then subtract the natural log of 15.3, and then divide it by 1.21 to the negative 4, which also has a negatives with it as you divide. And if you do all that, you will end up with something like this: 1.22377 equals minus 1.21 times 10 to minus 4. And again, dividing it over will give you a time of approximately 10113 years, about 10,000 years, give or take there. That's pretty old, yes, in that case, which makes sense. This is ancient, so that sounds good. question on that? So here we're solving for obviously time as we're looking for it here. Again, you want to just be careful of units, but you can put radioactive decay or rate of radioactive decay into this equation as well. Any questions on that one there? All right, so why don't you try the next one and see what you come up with. Let's take a look at it here. So they found a old civilization to be 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon for a rice that's found on the site? To see what you come up with here. And again, it's grams of carbon, so same half-life that we just used in the previous example, yeah. Gram of carbon. So we'll use our first order here. And here we do have the time, that's 15,600 years. We have our living, which again would be our initial, I'm assuming 20 counts per minute per gram of carbon. And in this case here, we're looking for what it would be at the end here for our rice, I think. And we have this, this, and this. Here we will use our half-life like we did before, which was our 5730 years. Once again, because it is carbon, obviously if it's some other element, you need to use the appropriate half-life if it wasn't carbon in this case. So we are going to get really the same decay constant that we got on the previous example there. And I believe that was 1.21 times 10 to the minus 4 years as our decay constant. So now that we have that, we can go in, we can go to the natural log of our final, which is what we're looking for, natural log of our 20 minus our 1.21 times 10 to the minus 4 years, and our time, which is 15,600 years. In this case, we're okay on units as they're both obviously in the units of years. So we'll clean up the right-hand side there. Why my button there? Natural log of 20 minus 1.21 to the minus 4 times 15,600 gets us a natural log of A is equal to 1.10813. Once again, going to take the E of both sides there. And that will give us our counts per minute here of about 3.03, again, counts per minute per gram of carbon, basically, right? And it does make sense since our living guy was 20, so this is obviously something that's been there for a while. So that should not be giving off as much, obviously, radioactivity here. So 3.03. Any questions on that? Yeah. It's based off of per grams of carbon, so it's really the carbon 14 one that we used previously here, that we got on the previous page there, I think. Whoops. So it's basically this guy right here. And that's what I was saying. So obviously, if it wasn't doing radiocarbon dating here, you would want to make sure that you use the appropriate half-life in that case. Any questions on that one there? All right, so now you should be professionals as you are. And on the final, when I ask you how old my double-double is, you'll be able to answer that question. Very good. And then the more important question of, do you still eat it? All right. All right. All right, so let's talk a little bit about where does the energy, I know you think I'm kidding, but that's probably going to be a question. When does the energy, where does the energy from fission come from? So remember that fission is really the process where we have a stable sort of nuclei or an unstable nuclei. If it's unstable, it will kind of do this. It will really decay and split off into a lot of times two new nucleuses. It oftentimes will give off a lot of neutrons in the process and energy in that process. And this can be spontaneous where it will just kind of do that. You could also, if you had more of a stable guy, you could kind of shoot a particle at it and kind of make it unstable and sort of initiate this process of happening. So there's kind of two ways that it can happen, sort of spontaneously and also through transmutation, which is sometimes referred to where you sort of shoot a particle at it and it gets a little upset that you just did that and it becomes unstable and will kind of go through a fission reaction. But sort of the hallmark of a fission reaction is you usually will create two new nucleuses. Won't always be the same ones created in a lot of cases. But the sort of hallmark of that is you get two new nucleuses. You definitely generate a number of neutrons in that process, and it usually releases a lot of energy. In the actual process of nuclear fission, there is some of the mass of the nucleus is actually converted into energy. So there's a slight discrepancy in terms of the atomic mass of the isotope and really the atomic mass of the nucleons, which is our protons and neutrons that's in the nucleus. And that slight mass difference actually gets converted into energy through our friend Einstein, I think is this equation here. And that's the energy is equal to the mass times c, which is the speed of light, which is 3 times 10 to the 8 meters per second. Unless you learn 2.9979 times 10 to the 8. Is that what you learned? Really, people really make nobody rounds anymore? I learned that like the other week. Like people like don't use the 3 anymore. I don't know why. I'm going to use 3 because I'm going to round. But if you like to still use 2.9979 times 10 to the 8, feel free to use that, I suppose. All right. So this slight mass difference is what is going to be converted into energy. This mass difference is what is referred to as the mass defect. So the mass defect is the difference again between really the atomic mass of the isotope and very much the particles that make up the nucleus. And that is what sort of gets converted in the process into some energy through this process. Why we use fission reactions? Fission reactions used for a number of things, including energy. And it does produce a lot more energy than even your, as it says up there, your most sort of exothermic chemical reaction will only produce something like 10 to the 6 joules of energy. This is like 10 to the 13. So you usually will produce a lot more energy. It's used in reactions in like nuclear power plants and other things because it does generate a lot of energy along the way. Now, that mass defect, as I mentioned, is really what gets converted, as I said, into energy. And the energy that's released when the nucleus forms is what's sometimes referred to as binding energy or nuclear binding energy. Nuclear binding energy is also used, as we'll talk about, as a measure of stability. So you could actually use nuclear binding energy as a measure of how stable a nucleus is. There's a couple of conversions that you could kind of use where you wouldn't have to necessarily use the Einstein equation there. And these two are sort of helpful. 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules. And 1 AMU, which is an atomic mass unit of mass defect, is equal to 931.5 mega electron volts. Now, the greater the binding energy per nucleon, the more stable something is. Once again, nucleons, pretty much your protons and your neutrons. Basically, what's found in the nucleus is what a nucleon is. So a lot of times when we calculate something like binding energy or nuclear binding energy, we do it per nucleon, and we use that number to look at stability and if something is more stable than something else based on their binding energy per nucleon. So let's take a look at one here, like our friend fluorine 19. And if we wanted to calculate the nuclear binding energy for this, we could do it again using both approaches. But the first thing that we would want to figure out here is really how many neutrons we have and how many protons we have. So obviously our number of neutrons here are going to be our mass number minus our atomic number, which means that we do have 10 neutrons. Our number of protons here will be obviously equal to our atomic number, which is 9. So to calculate the mass defect, which is again essentially the difference between the protons and neutrons mass and the mass of the actual isotope, which in this case has a mass of 18.9984 AMU. We will take the number of protons and we will multiply it by the atomic mass of a proton, which is 1.007825 AMU. And that is the atomic mass of a proton. We're going to add it to the 10 neutrons and times it by the atomic mass of a neutron, which is this number here in AMU. So that is the atomic mass of a neutron. We're then going to actually subtract it from the atomic mass of the isotope, which is a lot of times given to you in these problems, which is 18.9984 AMU. So if we do that math there, we're going to take 9 times 1.007825 plus 10 times 1.008665. We're going to subtract it from 18.9984. And that's going to essentially give us a mass defect of 0.1587 AMU. So this is the difference, again, between really the things that make up the nucleus and the mass of the isotope. And that is what's going to get converted into energy as this process goes through. Any questions up to that point? At this point, you could use, for old time's sake, our friend Einstein in his equation equals mc squared, where the m here is the mass defect, which is what we just calculated. So if we put that in there, that would get us 0.1587 AMU, 3 times 10 to the 8 meters per second squared. And that's going to give me about 1.428 times 10 to the 16. My units here are AMU, meters squared, second squared, right? Now, perhaps you remember that 1 joule is equal to a kilogram times a meter squared divided by a second squared, which means I'm pretty close to that, almost. So here I'm going to take my friend here, 6.022 times 10 to the 26, not 23, but 26 AMU per kilogram, because to the 23 is a mole in a gram, so to the 26 is a kilogram. See what I did there, I think, yeah. So thank you very much. So the AMU will cancel out there, so Avogadro's number to the 26 will get you to kilograms. And if we do that and divide by 6.022 to the 26, not 3, will give us 2.37 times 10 to the minus 11 kilograms meter squared second squared, which is the same thing as a joule. Any questions on that? Yeah. So these two here are just sort of constant values. They're the atomic mass of a proton and a neutron. They would be given to you, yeah. So they'd be given to you, and obviously you would use them, I suppose, in that case. Yeah. You don't have to memorize them. Other questions? Yeah.
How'd you go from the 18.99 to the 0.15?
I added all this here together and then subtracted it from this. So I took 9 times the 1.007 and then added to 10 times the 1.008. So that's basically the mass of really the protons and neutrons that are in the nucleus. And then I subtracted from the 18.9984, which was given to us as the atomic mass of this isotope. Yeah. And that's hopefully what you should end up with, I hope, yeah. At this point, though, usually binding energy is given in two forms, really. It's given in sometimes joules per nucleon. So a much better representation of this is we would actually divide this by the number of nucleons, which is the protons and neutrons that are present, which in this case is 19, right? Which is basically the mass number. And if I did that, that would be 2.37 divided by 19 would give me something like 1.25 times 10 to the minus 12 joules per nucleon. Now, another way that sometimes binding energy is given is in mega electron volts per nucleon. So I could also use some of that conversions that we saw earlier. Like there are 1.602 times 10 to the minus 13 joules per mega electron volt. And again, this was on the previous slide. And if we divide that by 1.602 to the negative 13, that's going to give us roughly 7.792 mega electron volts per nucleon, which is another way that binding energy is sort of given in terms of units. Mega electron volts per nucleon or joules per nucleon would give it. And this is a measure of stability. Again, the higher the number, the more stable it is. First off, any questions on that? So this is the way that you could do it if you wanted to use Einstein's equation. If you frankly did not want to use Einstein's equation, which maybe you don't want to use it, you could actually just use those conversions that we saw on the previous page there. So for example, here, if we we could pick up right about here where we've calculated the mass defect, and we could use that 1 AMU is 931.5 mega electron volts and go right into mega electron volts 0.1587 times 931.5 gives us 147.8 mega electron volts, which we then can divide by the nucleons, which are 19. And we will end up with pretty close to what we have on the bottom there, like 7.78. With rounding, it might be a little bit different, but pretty close to what we would end up there if we went that way. So you could go that way first if you want. And then if you wanted to change it to joules, use the same conversion to change it to joules. So you could do that by bypassing sort of Einstein's equation. And it's because those conversions are pretty much based on Einstein's equation. So you could kind of go that approach as well. Any questions on either of those there? All right, so let's take a look here. Here, as I mentioned before, we definitely can use our nuclear binding energy per nucleon as a measure of stability. And we actually see here it is iron 56 there. It's actually the highest in terms of binding energy per nucleon, which is the most stable. And obviously the smaller we have is less stable. So in here is where a lot of our fission and fusion guys end up, where we will get those unstable nuclei that will occur. Why don't you give one a try here? Calculate the mass defect and nuclear binding energy in mega electron volts. Let's do both, and joules per nucleon. For carbon 16 has a mass there of 16.014701. Once again, the proton is 1.007825 AMU, and the neutron's atomic mass 1008665 AMU. All right, so see what you come up with on that one there. Carbon is still number 6 on the periodic table. So So once again here, we probably want to start with neutrons and protons. So we have a mass number of 16. We got an atomic number there of 6. So our number of neutrons here would be 16 minus 6, which would give us not 6, but it would give us 10 maybe. Our number of protons there would be 6 in this case. So again, to take the mass defect, usually what you want to do in a lot of cases is to take the protons and neutrons minus the atomic mass that's given to you. Frankly, if you do it the other way, you'll probably get a negative number. And it's really, it has to do with all will be the same. It's just energy. If you think about energy, right, you have exothermic and endothermic, right? So positive or negative values that you could have for energy. It just means in one case, you're putting the atom together, or the nucleus together. In the other case, you're just breaking it apart. So that's what the negative, if you kind of did the other way, would sort of imply. So in this case, just to give us a positive number here, we're going to go with our 6 times our number of protons, which is 1.007825 AMU, plus 10 times 1.008665. And I'm going to subtract that from what was given to me as 16.014701. And again, this is going to give me that mass defect. A little bit's going to be converted into energy through this process here. And that will get me looks like 0.1189 AMU. Any questions so far? So since they wanted as well, when we wanted in both units, but the original question was mega electron volts, as I mentioned before, if you want to just use the conversions there, you could just go right into mega electron volts by using that conversion we saw there, which is 931.5 mega electron volts. So we would take that times it by 931.5, gives us about 110.8 mega electron volts, which at this point we could divide by our mass number, which would give us the number of nucleons. And we could get one of the answers that we're looking for, which in this case looks like 6.922 mega electron volts per nucleon. Question on that one there. Now we also wanted joules. So since I did it this way, I really could just use the other conversion and convert it out of mega electron volts to our joules. And if I did that there, we would times it by 1.602 to the minus 13. And that would give us something like 1.11 times 10 to the minus 12 joules per nucleon as well. So this way you can see you don't have to necessarily use the Avogadro's number or anything like that. But if you did that, you would get the same answer. You start with joules and work your way the other way. So it gives you a couple of different ways you can kind of do these problems. Any questions on that one there? Example, I think go to wrap this type of stuff up. Calculate the binding energy per nucleon. You could do mega electron volts per nucleon. That's good. For iron 56, atomic mass of it 55.93494. And that is lucky 26 iron on the periodic table there. Okay, so let's take a look. We're going to figure out our protons and neutrons. So once again, our neutron is going to be our mass number minus our atomic number. Looks like a 30 in this case. And again, our protons equal to our atomic number, which is 26. So to calculate our mass defect here, we're going to take each of those and multiply by the appropriate mass, 1.007825 for our protons, plus our 30 neutrons, 1.008665. All going to be subtracted from the mass there of the isotope, 55.93494. And that's going to give us our mass defect here of 0.5285, I think 0.5285 in this case. And again, that would be AMU. And since we're going for mega electron volts here, I'm just going to use the conversion, and that will get us right to where we need. So we're going to times it by our 931.5 mega electron volts there. And it looks like 492.3 mega electron volts. Once again, divided by the nucleon, which is essentially the mass number there, which is our protons and neutrons, and that would get us about 8.790 mega electron volts per nucleon. Question on that one there. So as I mentioned before, we could also use this as a measure of stability. So if we look back at the sort of three that we looked at, we have our iron 56 at 8.79 mega electron volts. We have our carbon 16 at 6.9. And we have our iron that we, not iron, our fluorine that we did at 7.7. So out of those three, it would be the iron that would be the most stable, which is actually the guy that we saw up here on this graph there, the iron 56, which is the most stable with that 8 point, whatever it was there in terms of its nuclear binding energy per nucleon, followed by the fluorine, and then obviously the carbon would be less. When did you use you can use the Einstein's equation on either of these if you wanted to. So for example, the one we just did there here, you could have taken this and went into equals mc squared, and you would do 0.5285 AMU and our 3 times 10 to the 8 meters per second squared. And if you did that, you would get 0.5285 times 3 to the 8 squared. That would get you something like 4.757 times 10 to the 16. And that would be AMU meter squared second squared. This is where you would then have to use Avogadro's number again to the 26th, which would get you kilograms. So you would divide it by 6.022 to the 26th, would get you 7.899 times 10 to the minus 11 joules, which at this point you could use that other conversion of 1.602 times 10 to the minus 13 joules per mega electron volt. That ideally would take you about there, and then you could divide. So it's a longer version. Those sort of conversions are basically based off of that, so it kind of allows you to do it without doing it. So it's really convenient, obviously, if you're going either way, really, either mega electron volts or joules, to kind of use those conversions, and they're based on Einstein's equation, or you can go that way with it and do it. Yeah. Other questions? Okay, so again, another measure of stability here, nuclear binding energy per nucleon. Again, the higher the binding energy per nucleon, the more stable it would be. All right, so let's finish talking about the rest of this chapter here, which is our nuclear transmutation. Transmutation is oftentimes when you basically shoot a particle at something and it gets a little upset and it sort of becomes something else. You could do that with a particle accelerator, which has a magnetic field, also an electrical field, and basically get the particle moving really fast, and you kind of shoot it at your intended target. And as this case here, we got some alpha particles and protons being shot at different nuclei. This is what is referred to as transmutation series, and it's those guys pretty much above 92 in terms of their atomic number on the periodic table. That's essentially how all the man-made elements are sort of made. All the ones with the good names like, you know, Einsteinium, Californium, Berkeleum, all those guys. They're basically made by, as you can see here, kind of shooting particles at other stable nuclei, and they will basically split off and basically become those sort of man-made guys. So in this process, it obviously goes through this fission process, which does give off a lot of energy, as we talked about. And through our transmutation here, for example, we can take a neutron like this, shoot it at a uranium-235. It's going to become upset, and also a bowling pin at uranium-236 there. And it's going to split off into a couple of new nucleuses there, and it will give off several neutrons in that process, as we talked about, and obviously a lot of energy is sort of given off in this. And in these sort of fission reactions, we'll talk about in just a second, this is sort of a problem that could arise from it, because as we can see here, kind of neutrons kick it off and you make neutrons, so this reaction could kind of keep going, basically, because you're making what you need to kind of keep the reaction going. As you can see there, if you took uranium-235 and went through this fission reaction, you would get something like 2 × 10⁻13 joules per mole. And that in comparison to 1 ton of coal, which only produces about 5 × 10⁷ joules. The comparison between these two is because coal is typically used for energy, right? That is historically how we get a lot of our energy, by burning coal, right? And using the energy that comes from burning coal. And this is also the reaction. The fission reaction is the reaction that occurs in a nuclear power plant, which is sort of the difference, obviously, between the two energy sources. Now, when we do this sort of process and have a fission process that occurs, we typically will get two sort of products produced, but they're not always going to be sort of the same products all the time. So you won't always, for example, here get strontium and xenon that will come off. There is a lot of similarity or predictability there of where in that range you'll get some of these guys, but it will not always be the same two that will sort of come off in this sort of fission reaction. So this fission reaction, in addition to nuclear power plants, also can be used in, say, like a nuclear bomb, and it can sometimes produce what is referred to as a nuclear chain reaction. And that essentially is the self-sustaining sequence of a nuclear fission reaction. So as I mentioned before, kind of to kick off this reaction, a lot of times you need a neutron, and then you produce more neutrons, which means it can kind of come back around and continue to allow this reaction to sort of propagate. In order for that to happen, you need a minimum amount of, say, for example, uranium or something like that, fissile material to have it sustain itself, and that is what's known as the critical mass. So there's a certain amount of material that you need to kick this reaction off and just let it go. So if you're in a non-critical sort of situation here, it's sort of a little bit under control here. It's not going to continuously sort of propagate. But if you do hit that critical mass, it is going to basically produce exponentially here. Every time it produces more neutrons, more radioactive byproducts, and more energy every time it kind of goes. So here, that's the idea between our sort of nuclear bomb here. You have a subcritical mass up on top, separated from the other part, the wedge. Obviously, when it hits, the wedge completes, and now you have a critical mass of fissile material, which will allow that reaction to continue on. Problem is, in addition to just the energy going off, right, it's producing a lot of radioactive material as the byproducts of those fission reactions, which is also giving off a lot of radioactive particles and rays and stuff like that, which obviously is what causes a lot of the radiation damage that obviously can be suffered as a result of that. Now, we also use this reaction in a nuclear power plant, and power plants pretty much, for the most part, traditional power plants, say nuclear power plants, work the same. Basically, there's water, you know, and basically you heat the water, and the water makes steam, right? And the steam goes out to the turbines, right? To your generators, and you get lights, yes, when you throw the switch and all that good stuff. So really the main difference between sort of a traditional power plant and a nuclear power plant is the source of the heat to heat the water. In a traditional power plant, you burn coal basically and use the energy that's coming off from the coal that's burning to heat the water. In a nuclear power plant, you're using a fission reaction to generate that heat to basically heat up the water. So when you look at a nuclear power plant, like by us, it's San Onofre, I think, right there off the freeway, the two big domes that you see. I don't think they're really operating too much anymore, but that's where they were here. And this is sort of what a nuclear power plant sliced in half, which doesn't sound like a good idea, looks like. It usually does have that really big, obviously cement sort of steel enforced dome. There's usually a chamber there where really the fission reaction takes place. And within here, you'll have several things. You'll have fuel rods, and fuel rods are really just like it sounds, rods with like pencil-sized erasers of uranium in there, basically. And that is the fuel, obviously, that's going to start the fission reaction. Fission reaction will happen. Obviously, we have some water in here, and it's in this sort of insulated container, which gets super hot from the energy from the fission reaction, which obviously heats out a bigger pile there of water. And that water obviously is going to produce the steam that goes out to the turbines and stuff like that. It's a good circuit because if you cool down the steam, it becomes water again, right? Which is why a lot of times nuclear power plants are located near large bodies of water because they needed to cool it. Unless you're inland, like in Arizona, then you have very big cooling towers of water kind of set up there, like the Palo Verde sort of power plant there off the 10 freeway. If you ever drove to Arizona, that's the sort of where theirs is. But they use it to cool so they could kind of recycle, obviously, the steam to the water and to do that. Now, in addition, you may be wondering, so why does this reaction perhaps not go crazy and out of control? And it doesn't go crazy and out of control because typically they keep it under a critical mass. So less than a critical mass is used. In addition, they also have control rods. And control rods are rods that are soaked in things like cadmium, which are neutron absorbers. So why would neutron absorbers be good in a fission reaction? Well, what really starts the reaction, right, is like a neutron, right? And you make neutrons, which then can kind of go back around and can keep the reaction going. So by having these control rods in there, they will grab out a lot of those neutrons from the reaction and keep it under control, so it can't just keep sort of exponentially growing and stuff like that. Usually, again, try to keep these things separated, but it does make a lot of byproducts as a result of this reaction. That's why they do have those control rods, and like Chernobyl, where they took out maybe too many of them and weren't able to put them back in very quickly enough. I don't truly know. I imagine there's some automation. I would imagine now a lot of these are actually shutting down because it's just too hard to come back up the code. So that's why like a lot of them electric companies are like, no, thank you. We'll use some other type of source. But I imagine years ago it's probably a combination of both. I would imagine. Yeah. Yeah.
Critical mass different for different materials.
It is. So depending on what it is, it will be different depending on the substances being used. So it's good in the sense that people would say it's good in the sense of nuclear power because it's clean energy, right? As opposed to cleanish energy, I guess is the way to say that, as opposed to burning coal, right? Burning coal obviously gives a lot of pollutants to the air and stuff like that, and you got to strip a lot of places to get the coal and to do that. But obviously there's downside obviously to nuclear fission reactions, right? Because obviously every time it goes through that fission reaction, you're creating byproducts that are around for a very, very long time, right? That are also very radioactive. So it does create a lot of waste, and a lot of problem was for a lot of years with nuclear power plants was what do you do with all this stuff, right? Where do you put it? Nobody wants it in their neighborhood, right? Nobody wants you like traveling to dump it in their neighborhood. So for a lot of years, they actually would just hang on to everything right there on site, and they kind of keep everything at the actual plant because nobody wants to take the waste. So I think in Nevada they built a big hole in the ground, right? And that's where they actually started using it, I think, several years ago. That's what powers all the neon lights there in Las Vegas, is that hole. But that's really a lot of the problems with that is there's what is sometimes referred to as spent fuel. So the byproducts of sort of the fission reaction, what's created is what's referred to as spent fuel. And that spent fuel is obviously very hot in a sense for a lot of years. As you can see, the spent fuel and years of how long it's still sort of active is a lot of years. So that also brought up a lot of issues of like, you know, who keeps a watch over for all these years, where do you store it in, and that type of issue. So there's good and bad, obviously, with both, and that's sort of the issue there as well. So let's talk a little bit about fusion. Nuclear fusion is a process where you take actually two smaller nuclei and you throw them together. And you throw them together in super high temperatures, like you're vacationing on the sun type temperatures. So really, really high temperatures is where that occurs. And isn't that why in all those science movies, they always wanted the scientist that did cold fusion, right? So you can go get that guy and all those spy movies. I guess it's not science movies, spy-ish. I mean, I guess they could be science movies, but spy type movies. I want the guy who created cold fusion. To finish up here, talk about nuclear chemistry. Obviously, we can use radioactive isotopes for a variety of things, including in the laboratory, but we could also use it in medicine as well. And clearly, if you're using it in a medicine, you're looking for some smaller half-lives, right? Otherwise, your follow-up appointment is a long time down the road, right? So here, obviously, hours, maybe minutes, maybe days occasionally. But for example, here, sodium can be used as a blood tracer. We have iodine, which could be used for brain imaging. The nice thing about radioactive versions of elements is that in the body, they basically do the exact same chemistry as non-radioactive elements. But the benefit of radioactivity is you could kind of highlight things, right? And you can see where it is and what's going on and that type of stuff. They also have, over the years, used just radioactive pellets and stuff like that to try to shrink tumors. They'll kind of insert it in there to shrink down tumors and stuff like that. So a lot of times it's used for imaging, as you can see here, technetium-99, a little bone scan will highlight a lot of things. And obviously you're looking for a smaller half-life. If you ever use radioactivity, that's your friend right there, your Geiger counter. It's a little guy, goes around and beeps, beep, beep, beep. Hopefully it doesn't beep too much as you pointed at yourself. But it basically measures radioactivity, and usually if you use it when you're done and while you're using it and after you clean up, you have to go around the lab and make sure you didn't make the whole lab radioactive and stuff like that. Also a great idea, you should always check your shoes, because people walk and spill things and you walk on in to go home, and then now you're glowing in the dark at home. So you don't want to do that. By the way, if I hold the Geiger counter up just in the air, will it go off? Will it make a noise? It will. There's background radiation, so it will go off, not loudly, hopefully, but it will tick a little bit, and that's something you sometimes hear people go, especially in labs where they don't want clean things up. Oh, it's just background. No worries, it's okay. That thing is loud. You could hear it in the other room. You might want to clean that up. All right. So lastly, here there's some biological effects that radiation can do to you, and that's what is sometimes referred to as a RAD, which is your radiation absorbed dose. Versus a REM, which is sort of the equivalent. And here's just a table where, you know, we pick up radiation along the way in our everyday life. You know, you get it from ground, X-rays, I guess, air travel, weapons testing, and nuclear waste, in case you live near there, I suppose. You get some of that. And obviously, the quality factors, basically a RAD times Q, and it has to do with the type of radioactivity that's happening there. As we saw in an earlier slide, depending on the emitter, for example, like gamma rays goes through very far, right? Penetrates very far. So it has a much lower factor than alpha particles, which does not penetrate as far. So you could get a little bit more exposure to that versus gamma rays. Obviously, if you're ever working with radioactivity, as we talked about earlier, you should always make sure you educate yourself as to what type of emitter it is. And they usually, again, used to make you wear like rings and badges. And every so often they would develop them to see how much exposure that you've had. And those are good things to keep in mind. Limit the time around the stuff is usually a very good idea. Any questions on any of that? That's strawberries.